Let us now see how to determine the band gap in a semiconductor diode. The apparatus that are required for this are a reverse biased diode, ammeter, thermometer, a heating arrangement for heating the diode, etc. As you all know, a diode in reverse bias condition will also have a saturation current. This means that when I study the reverse bias diode characteristics, as we increase the voltage across the diode under reverse bias condition, the current also increases, but at a particular voltage it reaches a saturation value for current, and beyond this, even if we increase the voltage, the current remains same. This means that the current has saturated to a particular value. Now this holds for a particular temperature, say room temperature, in which we perform the experiments. We now set the voltage across the diode at this particular voltage and immerse the diode, which is reverse biased, inside a heater. I'll be showing you now shortly where we are placing the heater in the actual instrument. So we immerse the reverse bias diode inside a heater so that we can heat the diode. So as we increase the temperature of the diode, the reverse saturation current also will increase. By studying this characteristic, we can relate the band gap of the semiconductor with the saturation current. The value of saturation current in the case of a reverse bias diode is Is equal to A exponential minus EV by kT, where A is a constant, K is the Boltzmann's constant, and T is absolute temperature at which we maintain the diode, and the V is going to be corresponding to the band gap of the semiconductor. This implies that log Is to the base 10 is equal to log A to the base 10 minus Eg by 2.303 kT, because 2.303 is to be multiplied for converting the exponential into log to the base 10. So Eg here is the band gap. Is here is in microamps, obviously because the diode is in reverse bias condition. The saturation current will be only in microamps. It will be a very small current. K is the Boltzmann's constant and its value is 8.616 into 10 power minus 5 electron volt per Kelvin. This implies that log Is to the base 10 is log A prime to the base 10 minus Eg into 10 power 6 by 2.303 K into T. This 10 power 6 has come into the numerator of this term because Is was in microamps, so Is, to convert it into amperes, we have to multiply by 10 power minus 6, and then when it comes to the other side, it will become divided by 10 power minus 6. That is why instead of A, we have put A prime here, and then in this side, this 10 power minus 6 in the denominator I have taken up, so it becomes 10 power 6. This implies that log Is to the base 10 is going to be log A prime to the base 10 minus Eg into 10 power 6 by 2.303 into 8.616 into 10 power minus 5 into T. This implies that log Is to the base 10 is equal to log A prime to the base 10 minus Eg into 10 to the power of 3 divided by T. Once you simplify using the values, I have taken the T also up. When T goes to the numerator, it becomes 1 by T. So this will be 10 cubed by T. So Eg divided by 0.198 and this into 10 cubed by t will be the value. Now when you look into this equation, right away we know the slope is going to be equal to Eg by 0.198 because it's an equation connecting Is and t, that is 1 by t in fact. So y equal to mx plus c, it is of that form, and in this case the slope m is Eg by 0.198. A graph can be drawn between the saturation current Is and 10 cubed by t, and it will be a straight line with a negative slope. So from that we get Eg is equal to 0.198 into slope from the graph. The slope from the graph will be delta of log Is to the base 10 divided by delta of 10 cubed by t, and hence the value of Eg is 0.198 into slope, and it will yield the value of band gap directly in electron volts. So here we see that we have all the connections in the circuit diagram already readily available. There is no necessity for connecting separately. So we have the circuit diagram also indicated here. You can see 3 volts DC is the voltage which we have fixed. We have a heater or an oven for heating up the diode. To read the temperature of the diode, we have a thermometer. So first what we do is switch on the power and also the oven. You can see that the light glow showing power on, and then also the oven. The current starts rising slowly. When the current reaches 50 microamps, almost, don't wait till it goes totally to 50, 2 divisions short of 50, when the current reaches, we switch off the oven, which means that we have stopped the heating of the diode. And when the current starts dropping from the value of near about 50, that is when it comes to 45, we record what is the temperature. Similarly, when it comes to 40, we record what is the temperature. So in steps of 5 microamps, as current reduces, we record the temperature. Now you can see the reading has reached 45 microamps. So do not switch off the power now, just simply switch off the oven. When you switch off the oven, you have stopped heating the diode. So what will happen to current? It will start decreasing slowly. So when the current comes to 45, note the temperature in the thermometer. When it comes to 40, note the temperature. Likewise, up to 15 microamps, note the temperature in the tabular column provided. After you complete the experiment like this, switch off the power. The readings can be recorded as shown in the tabulation. So we have the first one as current in microamps, the saturation current. We fix the current values as 45 microamps, 40 microamps, 35, 30, 25, 20 and 15 microamps. Accordingly, at a current of 45 microamps, we can record what is the temperature and then convert the temperature into Kelvin. And as we have seen already, 10 cubed by T is what we have to take in the x-axis. We also calculate 10 cubed by T automatically. Now log of Is can also be calculated. Remember, this log of Is is going to be log of 45, which is already fixed. So before you come into the class, write down all these values. Don't come inside and write the values. Try to minimize your time by writing these values before you come into the class. We will now see a set of sample readings. Again, as for the previous experiments, I repeat that it may not be the same what you are going to get in the class. It's only a sample. So we see current is already written here, and then the temperature, and then 10 cube by T, and then log of IS. Using this data, we have to plot a graph. Now for plotting the graph, we take 10 cube by T on the x-axis and log of IS on the y-axis. Very often people make mistakes in drawing the graph. We'll first see how we are going to take the x-axis and how we are going to take the y-axis. So on the y-axis we need to take log IS. Make full usage of the graph. For that what we do is take the highest reading, that is 1.6532, and then take the smallest reading 1.1760. When you subtract both, what you get? 0.5772. Now in the graph I have taken, we have 25 divisions. 25 divisions are there on this y-axis. So we have to divide this 25 divisions into 0.5772. So when you divide 0.5772 by 25, we will get approximately 0.02. So start with the least reading here, that is 0.176 is the least reading. So start your graph at 1.16. So in steps of 0.02 you can increase. So we have 1.16, 1.18, 1.20, 1.22, 1.24, etc. And you can see the last reading will be 1.66. What was our maximum reading? 1.65. So you can see you have made use of the whole graph. Do not use part of the graph, or don't take a reading lesser than 1.16 and mark in the graph. So you are simply wasting the graph and not using it at all, because those readings are not going to be there at all. So this is how you should plot the graph. And then for the x-axis in a similar fashion, we have the highest reading as 3.1948, the smallest reading as 3.0391. So the difference is 0.1557. And in the x-axis you have 19 divisions, approximate 19 divisions are there in the x-axis. So if you divide 0.1557 by 0.19, it comes to around 0.008. So you can take it as 0.01. Again start the graph at 3.02, not 2 or not 3, because your least reading is 3.04. You can start the scale at 3.03. So you have 3.04, 05, 3.06, 3.07, etc. And then it goes up to 3.22. So this is what you have as x-axis, and then mark the x-axis as 10 cube by T Kelvin inverse, log, and the y-axis as log IS in microamps. Now the scale also has to be written. Don't write 1 unit equal to something or 1 centimeter equal to 1 unit, etc. Specify clearly the x-axis. X-axis 1 centimeter equal to 0.01 Kelvin inverse. Y-axis 1 centimeter equal to 0.02 microamps. This is how you should draw the graph. Now using the data we have got, I have plotted the graph, and then you can see it is a straight line. You get points like this here. Round the points wherever you get. Don't leave it simply as a point, round it. And almost the points which coincide into a straight line, you can draw the line through that. Doesn't matter if some points are out or some points are just clustered around the line. You just have to draw a line passing through these points. It can be clustered around also. In fact, we have to really do a least square fit for these points. Once you have done this, you need to take the slope. I have taken a sample. You can see here the slope will be 1.456 minus 1.42 divided by 3.10 minus 3.09. So the slope here is 0.036 by 0.01, which gives you 3.6. So what is the band gap? 0.198 into 3.6, and that is going to be 0.7128 electron volts, or nearly it is 0.71 electron volts. So the band gap of the semiconductor you have found is 0.71 electron volt.